In this video, we're going to go through the special cases involving solving absolute value inequalities. The two first examples are done for you because that is exactly what you did in your last video, and these are just two basic extra example problems should you need them. You can see all my steps there, and then you can see how I've solved them, and then of course graph them on the number line. The biggest thing from last video about solving basic absolute value inequalities, one way to remember is that when you have less than or equal to, I want you to think less than, less the and. Now for greater than or equal to, greater, great, or. So these are just two little tricks to help you remember, because remember that the difference between an and an or is an and has to be the intersection where the shading overlaps. And with an or, that's a union, and that's just whatever happens, happens. See, the truth is that an and has to satisfy both arguments. So in that first example, x has to be everything less than 15, but also every number that is simultaneously greater than -5. And that's why it ends up being the overlap in the middle of those two numbers, which is pretty typical for an and. In an or, it doesn't matter what happens. If they go the same way, great. If they overlap, fine. If they don't, no big deal. It's just a this or a that to get a satisfactory answer, one that satisfies the argument. So focusing on special cases, this is especially when you get things that are atypical, like all real numbers or no solution, or in an and's case, whenever the shading goes the same way, you got to consider where the intersection truly is when it's not always in the middle like it usually is. So let's go down to our next example. We'll go ahead and handle the ands on the left-hand side, and then we'll handle the ors after that. Now I've marked this one as medium and special, so it's a special case. The first thing you need to remember is that you are going to have to isolate your bars. Before you can even tell me if it's officially an and or an or, you need to make sure you consider that the bars need to be by themselves. So when we update our problem, we have 2 times the absolute value of 2x plus 3 is less than or equal to 6x plus 10, because I moved that minus 10 over to the right-hand side. Again, I'm isolating those bars. Our next step will be to divide by 2 to both sides, which will then cross out those 2's. And we update our problem, which becomes the absolute value of 2x plus 3 is less than or equal to, well, 6x divided by 2 is 3x, and 10 divided by 2 is 5. So our final, we'll simplify it with the bars isolated, would be the absolute value of 2x plus 3 is less than or equal to 3x plus 5. So for space's sake, I'm going to reduce this down a little bit. I'm going to size this and kind of get it out of the way. See, now that you have this information, you need to drop the bars and write it twice. I'm also going to size this a little as well, so that you can finish solving your problem. If it's okay with y'all, I'm going to take this away altogether. So now that we have our problem completely ready, I can now categorize that is the absolute value is less than or equal to, so less than, less the and. So I know I'm going to be looking for the overlap of the shading when I have my two answers. Let's write those problems out. Remember, what you do is you drop the bars and write the problem twice. The second time you write the problem, you multiply one side by -1. Now when you do that, as you learned in the last video, that means not only do you change the, in this case, 3x plus 5 into a -3x minus 5, remember that when you multiply or divide any inequality by a -1 or a negative number in general, you must flip the symbol. So the second equation not only got its signs flipped on one side, it also got its symbol flipped and turned into a greater than or equal to. So now we're going to simply solve both inequalities. Remember that you have to get your x's together first. I'm going to subtract 2 x's. I have 3 is less than or equal to x plus 5. And now I can solve. I'm going to subtract 5 on both sides. Negative 2 is less than or equal to x. And on the other equation, instead of subtracting 2x, I'm going to add 3x. I'd rather have positives to work with than negatives. When I update my problem, that means 3x has been added to both sides, so 2x becomes 5x, and you end up with 5x plus 3 is greater than or equal to negative 5. I will then subtract the 3 and divide by 5 to get x by itself. Now that might seem like a really bad fraction. You've got x is greater than or equal to negative 8/5. If you really wanted to, you could certainly change that into a mixed number. 5 goes into 8 one time. That would be 3 left over, so you would have 3/5 left over. You can convert that 3/5 to a decimal, which would be 0.6, which in fact that's how I'm going to leave it today, because I want to be able to know easily where that number falls on a number line. So I'm going to go ahead and leave it in decimal form, though technically it doesn't matter. So we end up with negative 2 is less than or equal to x, and x is greater than or equal to negative 1.6. Now that first argument, that negative 2 is less than or equal to x, the truth is that if you flip it around so you actually read it from x's perspective, which is preferable, x on the left typically is how we like things, then you would have, if negative 2 is less than or equal to x, that means all of the x's are really greater than or equal to negative 2. I just flip the whole thing around. So I have x is everything greater than or equal to negative 2, and x is everything greater than or equal to negative 1.6. So when you have your number line, and you go ahead and just start doing a couple marks in both directions, no big deal. So remember, you need to get a visual before you make your final number line shading situation, especially with an and, because an or, whatever happens, happens, but an and is particular. It has to be the overlap. So I'm going to go ahead and map this out. If I have every x, as every number greater than or equal to negative 2, well, that would be a closed circle at negative 2, and it would be shaded to the right, every value for forever greater than or equal to negative 2. I also have this negative 1.6 that also gets a closed circle because it's got the or equal to, so somewhere around there-ish. You'll see it negative 1.6. And then I have every x also greater than or equal to the negative 1.6, so it also goes to the right for forever. So if an and is the overlap, where does all of it overlap? It does not overlap in between those two numbers like a typical and does. In this case, which makes it special, it overlaps everything to the right, everything greater than or equal to the negative 1.6. So the truth is, our answer is really only every x greater than or equal to negative 1.6, negative 8/5. So I'm going to do for my final answer, I'm going to do a closed circle at negative 1.6 as best as I can guess where it is on the number line. It's just an approximation. And then I will shade everything to the right for forever. So why is that special? Because ands are typically shading overlapping in the middle, and this one doesn't do that. It still overlaps though. It's still the right answer. It's just kind of weird, and that's okay. So let's go to the last example for an and then we'll switch to the ors. Automatically, before we even decide that this is an and, we have to isolate those bars. And then we'll make that decision. Even though we kind of have a hunch it's probably going to be an and because it's a less than symbol, that's not a guarantee. So I'm going to subtract 10. Update my problem. 8 times the absolute value of x plus 4 is less than negative 8. I will then divide by 8 on both sides. And update my problem. The absolute value of x plus 4 is less than negative 1. Now I want to make sure you understand the reason why that symbol, that inequality, the less than, did not change is because I didn't multiply or divide by a negative. I know the negative 8 was already there, but that's not what I multiplied by or divided by. I divided by a positive 8. You only change that symbol when you multiply or divide by a negative. Whether or not a negative was already there to begin with doesn't matter. It's not a part of the process. So this should be quick and easy. Now, for one, if you're catching it already, hopefully you recognize that there's already an issue because you know that absolute values must always be positive numbers. And positive numbers, last time I checked, are not less than negative numbers. So automatically we have a problem. Let's say, for example, though, that you didn't catch that. That's okay. If you know the process will still get you to the correct conclusion. So how you would finish this is this. You would drop the bars and write it twice. Noticing that since you have a less than, it makes you have an and. So you're looking for the overlap. So we're going to write and then we're going to write that second equation where you multiply the right-hand side, or any side in particular, but multiply the right-hand side by a negative 1, which not only turns that negative 1 to a positive 1, it also flips the less than to a greater than. Solving this one is, obviously clearly very easy. We're just going to subtract 4 in both cases. So x has to be less than negative 5, and simultaneously, after I subtract 4, x has to be greater than negative 3. If you stop and think about that, and you know that an and is the overlap, the shading's not going to overlap. I'll still prove it, but I want you to catch on that there is not a number on the entire number line that is going to be less than negative 5 to the left of negative 5, while at the same time being greater to the right of negative 3. It's not possible. So if you are not sure or not sold and you need a visual, that is not a problem. I need visuals all the time. So I'm going to go ahead and plot these, and we're going to talk about it briefly. If I'm just plotting these and getting ready, I would have an open circle at negative 5, and then I would shade everything to the left of that negative 5, because that's x is less than negative 5. At the same time, I would need to find the overlap with an open circle at negative 3 and everything shaded to the right. If there's no overlap, there's no solution. So the absolute truth, your answer is an empty number line, no shading. So you do not box this answer. That's a big no. Instead, you simply write no solution. If there's no overlap, there's no answer. So you do not do any shading, you don't do any open or closed circles. You simply conclude no solution and you move on. And if you really wanted to take away even I don't know why you would, because you don't, it's not that big of a deal. But you could certainly leave it completely empty if you really wanted to. That's just up to you. No hash marks, whatever you want. Okay. So those are our two examples of special cases with ands. So now it's time to go back and do some special cases with ors. Now, in this next example, which is, if you're looking on the page, technically the fourth example, if you're going from left to right as you progress through the page, you see the negative absolute value of 1/7 x plus 2 plus 5 is less than -3. It says medium / normal. The reason why this is normal is because it's going to have a normal OR. And typically the normal ORs, remember I know it's whatever happens, but typically ORs get split and they go in opposite directions. They don't have to, but that's just kind of typical. Now the reason why I have this still here on this page is I want to remind you what makes this just a tad special. When you look at this, if you're looking at the very beginning and you're seeing that you have a less than, you are going to be very tempted to immediately say that's going to be, oh, less than, less the and. It's an overlap. But this is on the right side of the page. And that was the whole, column of ORs. That's because you need to remember that you cannot draw the conclusion of whether or not it's an and or an or until you actually isolate the bars, get them all by themselves. So that's the first thing we're going to do. We're going to subtract 5 from both sides. So we have the negative absolute value of 1/7 x plus 2 is less than -8. The symbol has not changed yet because I didn't divide or multiply by a negative. It was just -3 and -5 combining together to make -8. So there's no change there. However, what comes next? Well, if this is really multiplying by a negative invisible 1 on the outside, to get rid of that, I'm going to divide by a -1. And that just so happens to switch your symbol. Less than becomes greater than, and that -8 becomes +8. And now we have greater, great, or. We're going to conclude that now we have an or. So this is actually an or the whole time, but you wouldn't have known that if you just made that an assumption in the very beginning. Be careful not to assume. Always do the math. It's totally worth it. So I'm going to size that down. Yeah. Okay. Actually, what I'm going to do is I'm going to put that over off to the side. And maybe size it a little more. Okay, so what are we really working with here? We are taking 1/7 x plus 2 without the bars, and we are saying it is greater than 8, or 1/7 x plus 2 that was going to bug me, is less than -8, because I would multiply for that second equation when I write it twice. I multiply by a -1, which is the symbol as well as the sign. So solving this is going to be pretty quick and easy. We're going to subtract 2 and update our problem. We have 1/7 x is greater than 6. And then remember, to get rid of a fraction, multiply by its reciprocal. So the reciprocal of 1/7, thankfully, is just 7/1. Just 7. It's beautiful. So we end up with x is everything greater than 42. Or, on the other side, we're again going to subtract 2. Update our problem. 1/7 x is less than -10. And then we'll multiply by the reciprocal of 1/7 to get rid of that fraction, which again is 7/1. So we end up with x is less than -70. So for this one, I'm not going to be able to draw this to scale on a number line. So just go with me on this one. We're going to take a little bit of a license here. So we have our final answers, and we need to put them on the number line. We can put them on directly, or we can think about it either way. So if we're not doing this to scale, then it's just going to be very basic. I'm going to put a 0 in the middle. I'm going to go over to where we're going to say is 42. Sure. I'm going to go to the left to where we're going to say is -70. Good enough. you would have an open circle at 42, shaded to the right because everything greater than 42 is going to be to the right. You will have an open circle at negative 70, shaded to the left because everything less than negative 70 is to the left. And there would be your final normal. If I said normal, it just means go separate ways because that's typical for ORs. So you'll have your normal OR. Remember, what makes this medium level difficulty is because you had to oscillate the bars, and that actually ended up switching this symbol, turning it from an and to an or, because you can't make that conclusion until you get the bars by themselves. So let's look at an OR that is going to be special. Again, we're going to have to isolate those bars before we do any sort of conclusion on if it's an and or an or, because it looks like to me it's going to start off as an and again because it's less than, and then of course we're going to change anyway. So let's update our problem. We have negative 5 times the absolute value of x minus 3 is less than 20. We are then going to divide by negative 5. And this is where the switch happens. When you update your problem, you have the absolute value of x minus 3, is now greater than negative 4 because you divided by negative 5 and that switches the inequality symbol. So great or greater, greater, greater or. It's unnecessary, I just realized. Okay, I'm going to take this out of the way again now that we have our problem. And let's finish it. Let's get that out of the way. Move that over here. Okay, rewriting our problem, dropping the bars, writing it twice. We have x minus 3 is greater than negative 4, or x minus 3 is less than positive 4 because we multiplied one side by a negative 1, and then that switched the symbol and the sign. Then this is going to be very quick and easy. And I realized I didn't even have to even shrink that at all. It would have totally fit. I wasn't paying enough attention. So add 3 to both sides. X is greater than negative 1, or, it's going to bug me, add 3 to both sides. X is less than 7. Okay, so let's talk this one through. If you're looking at a number line, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7, negative 8, negative 9, negative 10. Sure, good enough, whatever. All right, so you've got your number line. On this case, you would have x is greater than negative 1. So you have this open circle. I'm going to actually do it below it for now. An open circle with all the shading that would go to the right. When you have the 7, you have x is less than 7. So you would have this other open circle and everything less than goes to the left. Because an or is whatever happens, happens. When you actually put this on a number line, even if you were to start the negative 1 with the open circle like it should have, and you were to start the 7 with the open circle that it should have, when you shade to the right for that negative 1, it's going to fill in that circle on the negative 7. And the same is true whenever you actually have the open circle of the 7 and you're going to the left, it ends up shading right over that negative 1. So what ends up happening is the circles get filled in by the other arguments shading. So there's nothing open. The entire number line ends up being shaded because in ORs, whatever happens, happens. And if your answers literally only have to be any x that's greater than -1 or any x that's less than 7, any number will fit one of those two categories on that same number line. And it doesn't have to be simultaneous because that would be an and this is an or. So the final answer, we're not even going to put that right there. We're going to put all real numbers. Because your entire number line ended up being shaded. You want to show me the double-stemmed R? You certainly can. As an interval, that would be from negative to positive infinity, every number on the number line. If you even wanted to take away any of the hash marks that you see, and instead of doing an empty number line like the example that we just did a second ago, that is to the left, that was no solution, you would simply show me a number line that was completely shaded. That's it. So, all real numbers. Okay, 6 examples, 4 of whom were actually special cases. Yeah, 3 ish. If you need anything else, make sure you reach out and ask us. We are happy to help you. And I hope that this was helpful.